Right, all. Congratulations on making it through our unit. We are moving on to our next one. So I just want to do a quick review. I can't do it in present mode, so I'll just do it this way. So we learned about energy of molecules and how energy can transfer from one object to another through different ways, through touching of the molecules, which is conduction, through convection, which is where warmer molecules rise to the surface and push colder ones down so they can be heated up. And then finally by radiation, which is a type of wave that comes off of objects when they are moving. So just an example here, how a thermometer works is air molecules collide with thermometer and their movement energy is transferred to the mercury molecules inside of the thermometer. So when it's cold air, there's less kinetic energy or movement energies of the molecules in the air. And the air molecules don't hit the mercury as much and they don't pass as much movement energy to the mercury molecules. So the thermometer doesn't rise very much. Now, if it's warm outside, that means the air molecules in the air are moving faster. They have more energy, so it feels warmer because they're hitting us and they're transferring that energy to us and everything around them. So it is warmer. So when these are moving quicker, they hit the thermometer and they make the mercury rise. Okay. So another thing to remember is like heat can transfer through radiation waves. So this is an example of this little molecule in the bottom left starts moving quickly. And because it starts to move quickly, these little red lines represent invisible infrared waves of energy. And when they hit the next molecule, they cause it to speed up. So it's like this one's going fast, it sends little waves. It's this one, it starts moving fast, sends little waves. And that's how heat can get transferred. Now, one reason this is kind of important for us, besides surviving in the bighorns and keeping ourselves warm or our drinks warm or cold in our Yetis and hydro flasks is, it has to do with water. So these are H2 and O's. So there's the two H's, the two whites, and the O is in the middle. And this is an ice cube. So you can see that all the molecules are in kind of a cube pattern, and they're kind of vibrating because atoms are so small and the molecules they make up are so small. They're always vibrating because nothing is at absolute zero. Everything has a little bit of energy in it, a little bit of heat that it's giving off. So even ice that's really cold is slowly vibrating. Now we wanted to learn about thermal energy because we're going to start talking about water, especially how water can change. So there are three states of matter that hopefully you remember from elementary school or just living in our world. Okay, we have solids, liquids, and gases. And within solids, liquids, and gases, okay, their molecule arrangement is a little different. Okay, and it all has to do with thermal energy. So in ice, you can see that all the water molecules are connected together and they just kind of vibrate in place. Okay, they don't have that much thermal energy. Now, if you add energy, okay, it's called melting, they actually start to slide around. So instead of vibrating in place, they start to move around each other. Okay, they have more movement. They're still touching, but they can move around. Okay, and if we add more thermal energy transfer, okay, it's called evaporation, they actually become water vapor, which is an invisible gas in the air. So they kind of, instead of vibrating in place or sliding around, now they're all over the place because they have enough energy. Now, energy can also be removed. So if those water vapor molecules in the air are going fast and they're hitting things, they're giving away their energy, they slow back down into a liquid. And that's called condensation. Okay, that's when water vapor in the air becomes a liquid. So if you ever have a glass of water out on a hot day, you'll see water vapor condense on the outside of your glass. Now, if liquid water, if we remove even more energy, they'll stop sliding around and then they freeze, and that's ice. Okay, so thermal energy is why we have the three states of water. Now another image to show you that a little more in depth. This is more of a drawing. Okay, so you can see a solid, the molecules are vibrating, but they're in place. They keep their shape. Okay, if I were to drop a solid into a container, it's not going to change shape. It's going to stay its shape, okay, and the molecules just vibrate in place. Now, if we add energy, okay, they become a liquid. Now, liquids take the shape of their container, but they have a certain volume. Okay, they take up a certain amount of space. So they're kind of moving around each other here, but they fill up the container. Okay. If we had more energy, then they become a gas, and gases are all over the place. They wouldn't even stay in the container. They go everywhere. Okay. They fill the volume of the space that they're in. And then we can do the same thing. We can remove energy, make them liquid again, remove energy, make them solids again. So our last one, just to show you a little more scientific model of it. Here is a solid in a Erlenmeyer flask. You can see it's like in a little chunk in the middle of the container, and all the molecules are arranged and connected together, not moving very much, vibrating a little bit. Okay, liquids take the shape of their container, okay, but they don't fill it. They have gravity pulling on them because they're all connected to each other. They're not moving fast enough. So they're like sliding around and moving around at the bottom. Then finally, if we were to put a gas into this Erlenmeyer flask and seal it off, they're moving around so quickly that they just fill the entire container. Okay. So that's just a little rundown on states of matter. So the reason we needed to know states of matter is I want to show you something a little alarming about how much water there is actually for us to use on Earth. So watch this. This 1,000 milliliters represents all the water on Earth. I took out 30 milliliters. This represents all of the fresh water on Earth. 970 milliliters would still be salt water. Out of that 30 milliliters of fresh water that is on Earth, about 24 of it is wrapped up in glaciers or frozen. About 6 of it is in underground water sources or aquifers or unavailable for humans. And about 1 milliliter is in rivers and lakes and reservoirs and available for us to use. So out of all the water on Earth, we only get to use 1 drop. Don't you just love water? I know I do. So I'm really glad that I'm here on Earth, the water planet. Right now, we, as far as we know, are the only advanced life forms in the universe because our planet has this remarkable stuff, H2O. So our big question for Unit 7, or one of them, is are we going to be okay? Is there always going to be enough water for all of the people? Our population grows more and more every day, and we keep doing more and more things that might make our water not be as available to us. And that's why it's important to know about thermal energy transfer, because water moves through weird cycles. It's not always like this. Okay, depending on its thermal energy, it can be in the air. There's some around me right now in the air. Or it can be solid, like ice cubes, like you did your experiment on. So, I mean, if you just look at Earth from space, you can probably estimate how much of the surface is made of water. I mean, if you look, all the blue is water, it's most of it. Okay, so water can be found in mainly 2 different ways. It is salt water, which is H2O like this, mixed with another molecule called NaCl, or salt. Now, we can't drink salt water, and most creatures on the planet cannot drink salt water either, any that live on land. It won't hydrate us. The salt actually takes the water back out. So in the ocean, it's salt water. Okay, in a pond, it'd probably be fresh water. Okay, in a lake, fresh water. In a river, like these Tetons in Wyoming, also fresh water. In a marsh, fresh water. underground, okay, from rainwater seeping into the ground and the layers of the earth and from our streams. Those are also fresh water. Okay, glaciers, fresh water. Okay, when you freeze water, the ice or the salt falls out and you're left with fresh water. Sea ice actually is mostly fresh water, frozen. There's no salt really in the ice, maybe a little bit on the edges, but mostly fresh. Icebergs, even though they're in the ocean, again, they're mostly fresh water. So after looking at all this, you're probably like, there's plenty. There's so many different sources of fresh water out there. As you saw from my demonstration, the oceans are just so big. And most of our fresh water is constantly moving towards those oceans. So of all the water on Earth, 97% is salty in the ocean. That's what that 970 milliliters I showed you was. Okay. Of the 3% of the fresh water that's left, 68.7% is in ice caps and glaciers. 30% more, which is the smaller amount that we couldn't get to, is found in groundwater. Okay, there's other, which are some other sources of water like living things. Okay, surface water, it's only 0.3%. There's only 0.3% of Earth's water is this stuff we can get to on the surface. And of that, 87% is in lakes, 11% in swamps, only 2% in rivers. So we can see there's 3 different states of water. There's solids like snow or ice. There's water vapor that's in the air and the atmosphere around us. And then there's liquid water like in the oceans and lakes and swamps. Okay? So my question for you to go onto Google Classroom and discuss is, do you think we are ever going to run out or be in short supply of fresh, usable water? So you can think about, discuss it with your classmates.